video 5 of our chapter, we're going to get a little bit away from proofs, which I'm sure I'm hearing some applause now. Yes, 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 I hear some applause. We're going to get a little bit away from proofs, and we're going to start doing some more applied problems, if you will. We will still talk about theorems and stuff, but we will be focusing more on the calculation part of what we could do with our congruent triangle stuff. So in this video, we're going to focus on properties of isosceles and equilateral triangles. So what made an isosceles triangle so unique was that it had two congruent sides. Okay, and we're going to give some names to those sides and other certain features of an isosceles triangle. So we have 4 different vocabulary terms here. The vertex angle up top here, it specifically is the angle between the two congruent sides of the isosceles triangle. Okay, so here's one side, here's the second side that's congruent. The side, or not the side, the angle that is included, remember that term from this chapter, the included angle between these two congruent sides is specifically the vertex angle. Okay, so that will be an important term to keep in mind because we will refer to things in some theorems later on as a vertex angle. And if I go too fast as I'm flipping through these, you always have the option of pausing the video and finishing writing the things down so that you can continue on. So the next thing on our list are the legs, and the legs are the two sides that are congruent in our isosceles triangle. The base down here, this is really the third side of the isosceles triangle. It's that non-congruent side of the isosceles triangle. It's the one that's left out. Okay? And then base angles, well, those, notice there are 2 of them. There's only one vertex angle, but 2 base angles. They're the 2 angles that are opposite of our 2 congruent sides, which will play an important role of that location. So for example, if here's one leg, then the angle that is on the opposite side of that side, this is one base angle here. And then if we were to look at our other congruent side of our isosceles triangle, the angle that's opposite of it is our other base angle. Okay, so it's basically the 2 angles that's not the vertex angle, as another way to look at it. The base angles, another way to say it, would be the 2 angles that are adjacent to the base itself. Okay, the base is the included side between the base angles. So there's a few different ways we could interpret the base angles. The one that I want you to pay close attention to is that they are the angles opposite of our congruent isosceles sides here. So a couple theorems that we're not going to look at the proofs, yay, is theorem 4.3 and 4.4. And 4.3 specifically has the name of the isosceles triangle theorem. And it just says that if 2 sides of a triangle are congruent, aka it's an isosceles triangle, then the angles opposite of those sides are congruent. So they're saying that if we've got, in this picture, AC is congruent to CB, it is isosceles, then these angles, A and B, must also be congruent. Okay, and what name did we give to those angles, A and B? We called those the base angles. Okay, so if we have an isosceles triangle, the base angles are congruent. Now, theorem 4.4 is the converse of that. And the converse just meant that we flipped the if and the then part. So if you look up at 4.3, here's the if part. If we have an isosceles triangle, essentially, right? If we have 2 congruent sides, then what we concluded was that the base angles were congruent. Now we're literally going to flip-flop those things. We're going to say if the 2 angles of a triangle are congruent, aka if the base angles are congruent, then what we may conclude is that in fact that triangle must be isosceles. It must have 2 congruent sides. Okay, so notice in this picture, this is starting out with 2 congruent base angles. Well, that must mean that the sides opposite of those angles must also be congruent, aka those were the legs in terms of vocabulary. So we're not going to look at the proofs of those, and the proofs, they get a little weird because it relies on the fact that isosceles triangles are symmetrical, and so by drawing in the line of symmetry, there are certain things that we are kind of assuming are true to be able to do this proof. Essentially, to prove that the base angles are congruent and to prove that the legs are congruent, In the end, we would be proving that those were true with CPCTC from the last chapter. But we're not going to dive too much into that. But that's why these theorems work. So let's look at some actual applied problems here. So it says solve for x in example 1, and I look and I've got 3 sides and they all have x in common. So it doesn't really tell me much here. It doesn't tell me which sides are equal that I could set equal to each other. But notice the congruent angle markings. If I have 2 congruent angles, that means I have 2 congruent sides. Thus, it is isosceles. Now, which sides are the ones that are congruent? We need to look at the sides opposite of those angles. So it's saying that this side, the 4x minus 23, and the 65 minus 7x side, that those must in fact be our congruent sides. So we will set them equal to each other. And let's solve for x. So first thing I'm going to do here, I will add the 7x over. And at the same time, I'm going to add the 23 over to the opposite side. So that I've got 11x equals 88. Which after I divide my 11 over, I get that x is 8. And if I wanted to double check to make sure that these really were congruent sides, 4 times 8 minus 23, let's see, that's 32 minus 23, which is 9. So this side is really 9. And 65 minus 7 times 8, 7 times 8 is 56, and 65 minus 56 is 9. So you might be wondering, what significance did the 8x minus 57 side have in all this? Nothing. It had nothing to do with this problem. It was a distractor, if you will. Now, I could have said in this problem, solve for the length of the base of the equilateral triangle. And you might have to go, well, which side's the base? Well, the base is the side between the 2 base angles. And so in order to figure out how long the base is, you would need to figure out the lengths of the isosceles sides, the legs here, to take x equals 8, plug it in, to get that this is 64 minus 57, which means the base is really 7. And the legs are both 9. So that could be a question that I ask that's like this. So the 8x minus 57 in this example was a distractor, but it doesn't always have to be an example. All right, second example. Calculate angles DE and F. So as I'm looking at this, I'm saying, all right, this angle E, it's x plus 20, and D is 3x. F, they didn't tell me. Okay, awesome, thanks. But one thing I notice here is we have an isosceles triangle. We have 2 congruent sides. And by Theorem 4.3, the isosceles triangle theorem, that told us that the angles opposite of those 2 sides must be congruent angles. So if angle E is x plus 20, then that means that angle F is also x plus 20. So we can write that in there. Now we have 3 angles of a triangle. They all have x's in them. What do we know about the 3 angles of a triangle? Is that they must all add up to be 180 degrees. So we take the 2 x plus 20s plus the 3x, and you don't really need the parentheses here. I'm just showing you that, for example, this is angle, we'll say F, and I'm going to add angle E, and I added angle D here, that I really should get 180 degrees by the triangle angle sum theorem. So once I simplify all this, I should get 5x plus 40 equals 180. Subtract the 40 over, and we get 140, and divide by the 5, and we get 28. Now, I don't stop there. It didn't just say solve for x. It said, what are actual angles DE and F? So now I get to plug them back in. So angle F, I'm just going to do this, angle F, if I put in 28 for x, I get angle F is 48 degrees. And angle E, just throw an angle sign in front of it, is also 48 degrees. And angle D is 3 times 28, which would give me, 84 degrees. And there are my 3 answers that I'm looking for. And you could add together 48, 48, and 84 and see that in fact they do add up to be 180 degrees. Now example 3, I want you guys to do. I want you guys to try this one. So if you want to pause the video, you can pause it, work on it, and see if you can figure out how big values M and N are. The one thing I want to point out to you in this example is that there are technically 2 different triangles going on here. There's this guy right here, and notice it has two congruent markings on these two sides, so it's isosceles. And technically, there's also the overall big triangle. Again, notice there are two congruent sides, so itself is isosceles. So again, I'll have you guys try this one on your own. Now, Theorem 4.5 really doesn't have a name, but it says the bisector of the vertex angle, and here's our vertex angle up here in between our two legs, that if we were to bisect the vertex angle, that the bisector of the vertex angle in isosceles triangle is the perpendicular bisector of the base. So not only is the bisector of the vertex angle, not only is it bisecting up here, but it's also perpendicular to the base and it bisects the base. There's two things going on with it. Now, this was problem 15 that we did together in class out of your homework from section 4.4 from the CPCTC section. This is essentially Theorem 4.5, right? It says that if we had the bisector of the vertex angle, well, of an isosceles triangle, they told us we've got two congruent sides, which means this is an isosceles triangle. And we bisected this angle ABC, which happens to be the vertex angle. So what does that mean is true now? Notice how that and that really match up. Yes, we have different letters here. Really, the C and the B, if you notice, are flip-flopped from the example in the book to the actual theorem in the book. But we've already proved this. And remember, this was the proof that took like 12 lines to figure out. We're not going to reprove this because we've already done it. It was number 15 back from section 4.4. So, occasionally you'll run into some questions where you can use Theorem 4.5. Not really a huge thing, but it does come in handy every once in a while. So we move on. Equilateral triangles now. Everything that we just did with isosceles essentially works in its own special way with equilateral triangles. So equilateral triangles, all three sides were congruent. Okay? So isosceles, two of them are congruent, and an equilateral, all three are congruent. And so now we start talking about these things called corollaries. And a corollary is nothing more than just a statement that follows or is very similar to a theorem that we've already talked about. So when they say a corollary to Theorem 4.3, Theorem 4.3 was the isosceles triangle theorem. Well, this is just saying that we can similarly use this theorem of the isosceles triangle theorem for equilateral triangles. Okay? So this just says that if you have an equilateral triangle and all three sides are the same, then that just means that all three angles opposite of those three sides are also congruent. And what specific value will those three angles have? Because we're limited to 180 degrees, they must all equal 60 degrees essentially, right? We can also look at the converse of that and say, well, if we had a triangle that all three angles were equal, which they would have to be 60 degrees, right? That means that all three sides opposite of those three angles must in fact be congruent, thus making it equilateral. So if you have an equilateral triangle, it's equiangular. If it's equiangular, it's equilateral. So these two theorems really work forwards and backwards to each other. So for example 5, it says solve for x and the length of each side of the triangle. So if I look at this triangle, I notice each side has some x's in it, but the one thing I notice that I know for certain is that all three of these angles are congruent, which means I have an equiangular triangle. And if I have an equiangular triangle, then all three of these sides opposite of each other are equal. Well, which two sides do I set equal to each other? Does it matter? It doesn't. So let me just show you two possibilities here. Let's say I take the 3x plus 7 side and the 5x minus 3 side, and I solve for x. So let's say I subtract the 3x over, I get 2x. I add the 3 over to the 7 and get 10, and I find out x is 5. Okay. Now it also wants to know the length of each side of the triangle. So we'd plug that back in. 5 times 25, or 5 times 5 here is 25, minus 3 means this side's 22. 3 times 5 over here is 15. 15 plus 7 is 22. And 6 times 5 is 30, minus 8 is, 22. Now, let me put a little partition here. What if instead we had picked the 6x minus 8 side and the 5x minus 3 side? Well, let's see. I'd subtract 5x over and I get x, and I add the 8 over, and negative 3 plus 8 makes 5. I still get the same answer of x equals 5, and I plug it back in. I'm still going to get 22's again. And we could even go the last extreme here and say, all right, what if I had picked the 6x minus 8 side and the 3x plus 7 side? Well, I subtract the 3x over and I get 3x on the left. I add the 8 over with the 7 and I get 15. Divide the 3, and I still get x equals 5. So it doesn't matter which scenario you pick, which two sides. If you know they're all equal, just pick any two and you'll be good. Now the last example I want you guys to do, and again I will point out to you that this is a triangle that has 3 congruent sides. So if a triangle has 3 congruent sides, think about what must be true about the angles. And at first you might go, whoa, 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 whoa. We've got x, y's, and z's here? How can we do this problem? Just think about what those angles need to be and figure out what x, y, and z are. And that's the end of video 5.